Okay, so we can start. Yeah. So today we will do Wasserstein GAN. So this is another variant of GAN. And to do this, I will recall a little bit of the convex optimization. So, and in particular duality. So I will do this very quickly. So if we are given an optimization problem, so let me say it's a brief review of duality. So given an optimization problem, minimize f node x subject to f I x less than equal to 0 and h I x equals to 0, I equal 1 to m, and here I equal to p. So this is an optimization problem with inequality constraints and equality constraints, and to solve such a constraint optimization problem, we use sometimes we use something called duality. So I can form a dual of this, and so before that I construct something called Lagrangian and introduce some multiplier for inequality and equality constraints. Okay. So I construct a function x lambda nu, and this is f node x plus sum of, let's say, lambda I fi plus sum of, let's say, nu I h I x. Okay, so this is called Lagrangian. It's the name of a mathematician. So, and we can construct a dual function which will be obtained by infimizing this. So I can construct a dual function which will be g lambda nu, and this is infimum over x of L x lambda nu. And we can solve a dual optimization problem in the sense that we can do a supremum of this over lambda star nu star, and what we know from optimization method is so from convex optimization, what we know is g lambda nu is less than equal to f node x. Okay, so g. Okay, we can prove that. Okay, so you can say that it's an exercise for you. We usually do this in optimization method. So what this suggests is that to solve the minimization problem, if I have a primal problem which is p star, and then I go to the primal via xi, and this is my g lambda nu, and I can approach to the primal p star via lambda I nu I. Okay, so this is the duality in optimization method, where you solve a given problem via constructing a dual function, and then you can maximize that. Okay, so you do a supremum of g lambda nu, okay, over lambda and nu. Okay, and that way you can approach p star. Okay, so this is a very brief about optimization method, in particular duality. Now, yeah, so I think that should be and let us say d star is the dual optimal. Okay, so let us say d star is the maximum you can get. Okay, so let us say this is p star d star, and minimum or infimum, okay, it's f node x, we denote it as p star. So one question in optimization method is when are these two equal? Okay. So in general, I know that D star is less than equal to P star. Okay. So that's obvious because this holds. So clearly, D star is less than equal to P star, and this is called weak duality. Now, an obvious question is when D star is equal to P star, right? That will be the case when I will solve the given problem via dual and I will get to the primal. So when D star is equal to P star, then it's called strong duality. Okay. So these are very brief about that. And what we need from all this for the WGAN is strong duality allows you to do interchange inf and sup. Okay, because if you see G lambda nu, then G lambda nu itself has an inf inside. So what you are asking is what are the cases where sup inf and inf sup can interchange, and apparently this is possible when strong duality holds. So we have to look into that argument. So min max characterization of of weak strong duality. Okay, because we will need that in WGAN, where we will need to interchange. Okay, so let us consider a case where there are, for simplicity, let us consider a case where there is no equality, just this case. Okay, and as an exercise, we can extend this to this case. The fact that I can interchange inf and sup, let us do it for a case. So consider only the f naught x subject to fi x is less than equal to 0. Now for this, I want to develop a min max characterization. So as I said, I mean, if you look into the Lagrangian, and the dual function that I get is after infimizing over x. But if I have to interchange, then I'm actually asking what about supremum of L over x. Okay, so let us see this case, which looks like it may not be useful, because what we were taught is like you should take the inf and then do the sup of G. But let us do the other way. Let us do the sup of this. So note that so we can do this here. Sup of lambda greater than equal to 0 L x lambda. Okay, since there are only inequality constraints, I got rid of the nu and we have only lambda. So this is sup of, we just put the L lambda, and then L in this case is, the Lagrangian in this case is with only inequality. So plus sum of lambda I fi x, I equal 1 to m, I guess. Right. So we are supposed to do sup of this. Now what could be the sup of this, right? Lambda i's are greater than or equal to 0, fi's are less than or equal to 0. So overall, these guys are less than or equal to 0. This is because lambda i's are greater than or equal to 0 and fi's are less than or equal to 0. So overall combined, this is less than or equal to 0. So you know that the sup of this can be at best f naught x. Okay, so this will be the f naught x, because yeah, lambda I you can choose to be 0, right? And so at best what you can do is f naught x, and so in this case f(ix) is less than equal to 0 and it's infinity otherwise. So if f(ix) are less than equal to 0, lambda is greater than equal to 0, that's already known. So the second term is definitely negative, and in that case the maximum I can get is f naught x. And what is the otherwise case? Otherwise case will capture anything that's not in the domain or whatever. Okay, so so this is our soup. So if x is not feasible, and that's what I said just now, like what is the infinity case, right? So the text is trying to say this. Okay, so suppose x is not feasible and f(ix) is greater than 0 for some I, then soup of lambda greater than equal to 0 L x lambda is infinity. It can be seen by choosing lambda j equals to 0, j not equal to I, and lambda I tending to infinity. Okay, in that case we can let the soup go to infinity. And the first case is, as I said, if everything is feasible, then fi is bounded above. That's what supremum is looking for. So upper bound is there, and this is like less than equal to 0. So in that case, everything is fine. We have the f naught. Okay, so this is the supremum. So what we observe from here is that by looking at this, our original problem was infimum of f naught, right? So it seems like to get p star, I have to do infimum. So infimum of supremum of this. So since I added infimum, here also I will put an infimum, and that gives me p star. So p star is infimum of supremum of this. So this implies p star is infimum of over x, supremum over lambda greater than equal to 0, and L x lambda. And from the definition of the dual function, that the obvious one is the d star was sup inf, right? So the d star, and we recall that, so if you need these references, like you can always look into Boyd convex optimization if you want to know more. I'm doing only that much that is needed. Okay, this is a book. So what the dual chapter tells us, that the obvious thing is d star is supremum infimum, d star is supremum over lambda and infimum over x of L x lambda. Obviously from here, right? Obviously from here what we see is if strong duality holds, right? So we can do both the cases, right? So weak duality told us that d star is less than equal to p star. So in that case, sup inf must be less than equal to inf sup. Okay. So the weak duality can now be expressed as weak duality would be interpreted as which means d star less than equal to p star is equivalent to saying that sup inf of L x lambda is less than equal to inf sup of lambda greater than equal to 0 L x lambda. This is weak duality, and strong duality will tell us that you can interchange inf and sup. So there will be equality there. So in this case, we have sup inf lambda x L x lambda is inf sup of L x lambda. Okay, so this is the quickest introduction to duality and strong duality, weak duality, and we need this last one, okay, when we can change. Now we will go to WGAN. So WGAN is essentially a GAN itself. So you have min max again, okay, so it's a min max saddle point problem again, but it's a much more stable variant of GAN, okay. So just a quick recall of what we had in the previous GAN. We started with PR P theta. You can think of this as real distribution and estimated one, and this was PRX log PRX by P theta x dx. So this is the KL divergence, and as I said, you can derive multiple ways of generative modeling by changing the measure of the probabilities, right? So WGAN tries to do that. So that's another way of using some another measure, but it goes well beyond even F divergence, okay? So if you recall, the F divergence was PR P theta, and this was PR x F of P theta x by PR, okay? And this was a special case of the F divergence. So this belongs to family of F divergence, but WGAN uses something called Wasserstein distance, okay? So we will, it's also a probability measure, but does not belong to this class. And we also saw that minimizing KL is equivalent to MLE estimate, okay? I don't have to do this. We have done this in the last class. So there is a proof for that. Now, the main motivation for going to WGAN is to find out the deficiencies of this existing matrix, right? So one of the deficiency of the scale divergence is that it does not work on distributions that I mean, there is a technical way to say is that they don't have the same support, okay? By support we mean so support of a function is set of values in the domain of F where Fx is non-zero. So this essentially tells us that when we are looking into KL divergence, it also matters for which values of x these guys are defined, right? And we can clearly see some issues can arise if this is, I mean, not defined, or let's say 0, right? If this guy becomes 0 for that x for which this is non-zero, then it's not defined, okay? Because then this log of infinity, right? So then it doesn't make sense in that case. Log of 0 is also not defined. So there are clearly problems where both distributions may not match, right? So in a graphically we can think of the probability distribution P is like this, whereas the another probability distribution that I have is, so these are the values for which this P is defined, but then I can have another probability distribution like this, okay? So although where they overlap it's fine, but the places where they don't overlap, For instance, if I have to compute the KL divergence for these values, okay, then it will be problematic. But yeah, even more is like this, like they are completely separated, right? So in this case, KL divergence will always tell you that they are infinitely apart. Okay, so KL is infinity for this. KL is give you infinity value because the distribution Q for which the support is this and distribution P where the support is this, they don't intersect. This exactly means is that there are X for which P is 0, P theta is 0, but this is not 0. So then we get an infinity, or we have a log 0 which also gives you infinity. Okay, so KL divergence has this issue, and where the two distribution support don't match, then KL divergence goes to infinity. But this in general shouldn't be the case. So we are looking for measures which does not explode in such cases, but still give me some way to compare. Okay, some distance measure I still want in that case, even if their support is not the same. Okay, so that's where WGAN comes in picture. Okay, so how can you resolve problems with KL divergence, right? And this kind of distributions can happen in certain applications, like if you're working with text data. So you sample some words, but some words are very infrequent. In your true distributions, they have some probability value, but the actual sample will never show up. So there are very explicit, very like rare words in our dictionary that we usually don't encounter, right? So if you start comparing, then each time the KL will become infinity. So obviously people have thought about that, right? Because so what they will do is that, okay, the problem seems to be this 0, so why not do so-called smoothing, right? So smoothing here means, so given a vector V, I have like this, then smoothing usually means that I make zeros perturb it by some epsilon, okay? So smoothing a vector means that I will add some epsilon so that they don't give me 0 values. So this kind of trick is done in NLP because that's a very big problem there. Many words are very rare, right? So smoothing can be done and then everything is well defined. But if you do the smoothing, then you are supposed to add some noise, right? And this noise should have a high bandwidth, like that. And I also added a noise for this guy, okay? Just like making zeros non-zero, but then I also lifted these guys a little bit. So I added a noise just like this noise I'm talking about. In this case, it was a epsilon noise, right? And this epsilon can also change if you want, okay? So this could be epsilon from some standard normal and something like that with high bandwidth. So that should not itself be a noise that looks like this. Then it didn't help, right? So you need so that you cover this broadly enough. So smoothing can be done for KL divergence, and in fact this is what people do and they make it work, okay? But there are issues with the fact that the very fact that you add these epsilons, they create a error, explicit error that essentially you are adding by hand, and that will create issue at some point, right? So we are looking for a clever way of measuring such PDF where they may not have the same support, okay? So that's the main motivation we had behind WGAN. But then WGAN also has some other interesting things, that this measure satisfies triangular inequality, whereas KL didn't satisfy, okay? So there are quite a few advantages. So just to keep in the notes, KL divergence may become infinite if support of PR P theta does not match. So remedy is add a noise, as I said. But this noise degrades the quality, degrades the quality of samples. Okay, so even if it's image or something, there could be very minute thing in the image, and just because of this smoothing, you degrade that, right? So now let us look into WGAN. Okay, so the measure of the WGAN, what it is. Okay, so different distances. Just a quick recall that there are many other, but KL we have already seen, and Jensen's divergence we have already seen. Okay, so Jensen is a mix of KL and sometimes they KLK if you change, right, P and Q. So the new one could be total variation measure, or distance. So this is delta PR PG is supremum of A sigma PRA minus PGA. So this is essentially saying that you take the supremum of all the probability values that you can think of, differences of those. Okay, so this is called total variation. We have seen KL divergence, and let us directly define Wasserstein distance. Wasserstein we will focus on Wasserstein 1, just like LP norm we can have Wasserstein P distance as well, but in our case we will focus on, let us say, W1. And this is also very popularly called earth mover distance. There is a geometric interpretation of this. I will do this in the next class. Today I will prove an important result called Kantorovich duality, and today what I will do is that I will directly tell you the main idea, and all other proofs will be postponed to the next. So today I will just do exactly what I need to derive WGAN algorithm. Okay, so today will be like that. So for that we have a very major result, which is a duality theorem. Basically what we do in all this is that we start with a measure, okay, and then we develop some variational approach, right? That's what I said and so then we develop variational approach that involves min max, okay, and often there are some key ideas. For instance, in this case there was F divergence, and then there was a variational idea using the conjugate functions we introduced here that allowed us to use a variations in T. Now similar thing will be asked in this measure, other measures, right? How will you create this variational approach when the matrix changes, right? Here you used convex conjugate functions here, but you have to use some other tool, right? So same thing may not work. Okay, so again we will think of something like that. So let us define this WGAN, which obviously measures two distributions. So my notation sometimes changes, okay, but sometimes this is obvious, okay. Sometimes I write P and P theta, sometimes I write PR, PG, it's fine, okay, we know what it means. So this is infimum of gamma in PR, PG, and expectation over xy coming from gamma, and this is norm of x minus y. So in short, in words, what this is trying to say is that do an infimum of the expectation of the difference of x minus y, where x minus y are sampled from joint distribution. Okay, so we have seen joint distributions before in the probability class. So now we are sampling from some joint distribution, and it could be some joint distribution you can think of. Okay, and you infimize over all possible all samples x y which are taken from PR PG. Okay, so this is a joint of PR and PG. Okay, so there will be joint PDF basically, and from there I can generate samples pair x y. Okay, yeah, these are the collection of all possible joint PDF you can think of. Okay, the all possible joint distributions you can think of between PR and PG. This is a set. Okay, but once you have that set out of that, then you find the expectation of x y. So basically you have to do it for all. Okay, so pick some gamma which is a possible joint distribution of and then you sample x y from there and check whether norm x minus y is small. So you have to keep this. So basically for all possible. So right now it's abstract. Okay, obviously it's hard to say how to do this, right? It's a theoretical thing right now. So but we will make it specific. Okay, so this is in theory, this is how it is. So I will define this now. So pi is PR PG is set of all joint distributions. And these are your marginals, obviously, the way it's denoted. So I have a distribution given by joint fxy xy. Then I get a marginal by, if I have to calculate for the y, then I x, then I integrate out the y. So these are the things we have done in the class, right? So so this is joint xy, but then I have the corresponding marginals for x and for y. Okay, so PR and PG are the marginals for x and y. So the joint is, in this case, is like gamma, whose marginals are PR and PG. I will give you a better interpretation of all this, why it's called earth mover and so on. I will just write one statement today, but I will not go into that because I plan it for the next class. So this basically means how much mass I have to move to get from one distribution to another. Okay, so that literally this is what earth mover distance means. But we can play around with this with some examples in the next class. Okay, so the priority is to derive GAN. So here physically this means how much mass must be transported. So essentially all this is coming from even a broader topic. It's called optimal transport. Okay, okay, if you want, then this is Cedric Villani, field medalist, French. Okay, his book is the main reference. So what this says is that optimal transport is an even better framework to view how to compare probability distributions. Okay, so we will try to leave this for the moment for the next class. So there is a connection with the optimal transport, and this is why I am using this language, how much mass I move from, so that I can fit one distribution on the other, right? So that's why for the moment it may not be very clear, but we will do this next class. So how much mass must be transported from x to y to transform PR into PG. And the Wasserstein distance or the earth mover distance gives you the cost of that optimal plan that you are this is the cost that W gives me, okay, for moving via gamma xy, okay. So we will do this interpretation. So for the moment we take this WGAN measure as it is and focus on deriving the WGAN main idea. Okay. So the key idea again seems to be the same, which is so first of all the problem is again just like the KL divergence, here infimum is not easy, okay, not tractable, okay. So basically the expectation can be written as an integral, right, and this infimum is not tractable in practice and we will look for some variational approach. So estimation of inf where pi where gamma comes from PRPG, expectation of x minus y is intractable, okay, not possible to do this. I mean obviously like how much search I will do, right, over all possible distributions, joint distributions and so on, okay. So that's not doable in practice. So we have to do something that can be developed into algorithm. So here the key idea is again use duality to get a variational form. Okay, so that's why we did duality in the beginning today. That how constrained problem, right? We saw minimize f naught x subject to f I x less than equal to 0. So those are constraint problems. So in this case, what will happen is that obviously it's an optimization problem, but then while developing this into a tractable form, we will have to consider certain constraints, and then with those constraints we have to use the duality there, okay. So it may sound a little bit off right now, but let us do step by step. So use duality to get the variational form and reformulate W distance or W1 distance as a solution of max over one Lipschitz functions, okay. So basically Lipschitz functions are when a function is L Lipschitz is L Lipschitz if f(x minus f(y) is less than or equal to L x minus y. Okay. So this is f is L Lipschitz continuous if this happens, and what we will try to do is that we will formulate Wasserstein distance as a maximum over L Lipschitz functions, okay. So it does not look very trivial, right? So this is what we will do, and the third step is to turn WGAN, the fact that it will be a max over L Lipschitz, and since it's max over L Lipschitz, this ellipsis is a bound, the constraint we have, and so since it's one ellipsis, your L is 1. Okay, so what we are saying is that fx minus fy is less than equal to a norm of x minus y. So that's a constraint, but then that constraint I have to eliminate, and once I eliminate that, I will use the duality, and then I will get, so there is a max, and then will be one more min. We are looking for max and min, right? So let's see the process. So the turns WGAN into saddle point. And what is important as a researcher to know is the flow of the ideas, right? So what are the key ideas in WGAN? Variational approach, how it was brought. In this case, how it is brought into variational form. Okay, so the key idea is this variational form. So so this approach is similar to this. So now the main result that we have to complete today is Kantorovich-Rubinstein duality proof, and that turns the WGAN loss into the second point that I said, max over one ellipsis functions. Okay, so Kantorovich was a Russian guy. As usual, most fundamental ideas come from there. Kantorovich, Rubinstein, so according to this theorem, WPQ, okay, again I may keep changing these notations. Okay, now I'm using WPQ. Earlier I was using PG. Okay, it doesn't matter. These are not very complicated maths, right? So pi in pi PQ, expectation of xy. Again I changed, right? The gamma I was using before, now I changed to pi, just for a change, right? Sometimes we should keep changing. So x minus y. So this is our Wasserstein distance that we just introduced, and what this theorem says is that you can convert this into what I said is max of one ellipsis. Okay, so what this says is that this is equal to max or supremum. Okay, we use max when the max is achievable, but supremum may be, even max may not be achievable, but supremum may achieve. Okay, so there is a difference between max and supremum. So it is safe to say supremum because that always exists. Okay. Okay, so supremum of HL is less than equal to 1. So this denotes the one ellipsis continuity of the functions L. Okay, so this is supremum, and then expectation of Hx. So these Hx are the variations we are looking for. Okay, in the previous one it was T. So this is the main result of Kantorovich-Rubinstein, which says that Wasserstein distance, which looks very abstract as such. Okay, so infimum over all those joint and so on. This could be translated into a slightly simpler thing where I am doing supremum over H over just all one ellipsis functions. Okay. So compared to this, where I had to like do a lot of search and so on, here it seems like, okay, this seems a little bit tractable. The problem reduces to H L ellipsis functions. Okay, and doing supremum over that. Obviously, in practice, you may not get the exact equality, and that's never the intention anyway when we do computing. in computer science, we are always looking for something tractable which gives to practical idea. Okay, so obviously we will do approximation of these when we actually do it in practice. So now let us try to prove this theorem. So we are supposed to introduce Lagrangian and with the multipliers f and g, and these f and g are px will be marginal, that's right. So in this case p is marginal, q is marginal, which I get by integrating with respect to, and then f and g are the multiplier, right. So proof, right. So we note that P and Q are marginals for the joint pi, right. So what and this is a constraint, because that's a demand that I have, that all the joint that I'm considering are such that their marginals are P and Q. So the constraints that I have, okay, I'm just looking here right now, okay, because this is what I have to prove. So I'm looking here. So there is an implicit constraint here in terms of the marginal, and which says that I will write down as Px must be equal to, if I integrate the joint and integrate out the y. Okay, that's what it means, that Px is a marginal of the joint pi, then this must be true. And similarly, the other constraint is Qx must be obtained by integrating out the, okay, Px, then let us say it's Qy, okay, and this is obtained by integrating out the x. Okay, this is a constraint that we have. So now it's a problem of infimizing the expectation of x minus y with these equality constraints. Okay, so just like in the beginning we had equality constraints like hi x equals to 0. In this case, hi will be px minus this equal to 0. So in our case, if I have to set this as h, then this is h1x is defined as px minus pi xy dy equal to 0. This is the standard form, right? And if I have to write the another equality constraint that we have here, which is qy minus pi xy dx. So these are our equality constraints. Okay. Now we, since this is a problem with some constraints, it is obvious usually to invoke duality, right? So write a dual form of that. So since W PQ is a mean problem with equality constraints, so let us say that this is star. Constructing the Lagrangian this is called Lagrangian function, okay. So I have expectation there, right? So that will be integral of x minus y with the joint pi xy, and plus we introduce Lagrange multiplier. So we have to introduce Lagrange multiplier, right? So let us introduce the Lagrange. For each equality, I will have one Lagrange multiplier. So in this case, I will have lambda 1 and lambda 2. But the way I am using here is I call them f and g. as Lagrange multipliers. Okay, so introduce Lagrange multipliers. So with this setup, we can write the Lagrangian, and which will be given by L f g. This is integral of x minus y. This is the expectation term that we are writing, and the domain of all this, let us say, is some is x. Okay, and then pi. So joint PDF. Plus the equality constraint and the Lagrangian of those multipliers, right? So this is px minus pi xy dy, and this all goes with fx dx. So earlier I have shown you writing Lagrangian with the summations, but you change summation to integral here. Okay, that's the only change I have to do, because this is a continuous problem, so I change summation to integral. So this, you can think of these as h1, since these are equality constants, so you can think of these as mu1. That's what I did. Okay, and then I can do the other Lagrangian term here. So this is qy. Okay, I hope the notations are correct. Yeah, so qy minus integral over x pi xy dx, and this goes with gy as the Lagrange parameter dy. So this is the Lagrangian for the Wasserstein's distance, right? So collecting terms algebraically, so the first one, if you look into this, okay, so this again, like here, I can tell that this is h2 mu2 as a another factor. So let us collect this px fx dx, but px fx dx will be nothing but expectation of f, and qy gy dy will be nothing but expectation of gy, right, according to Lotus, right? So collecting terms algebraically, so that then we get L pi fg is expectation of x from q, and this is expectation of fx plus expectation of y coming from q, g of y, and plus the remaining terms, that the remaining terms all go with pi xy. So we have that those pi xy common now. So all goes with, remaining goes here, x minus y minus fx minus gy pi xy dy dx. So we have done this simple algebra to rearrange things. Our original goal is to have W, and W was an infimum problem with some equality constraint, and we change it to Lagrangian, and we know that the next step after this is to kind of infimize the Lagrangian and take a supremum over that, right? So that's a way to solve the given primal problem via the dual problem, right? So let us do that. Okay, so now the next step is that we will and the additional thing that we did was that it was not convenient for us to do sup inf, and we use the strong duality to change to inf sup. So, using strong duality, okay, now one of the things is like we are assuming that strong duality holds. Okay. So, there are certain conditions under which strong duality holds, okay, and whether that exactly gets satisfied here I am not even checking, not even the literature is checking all this. So, this derivation itself may be already introducing some approximation. Okay. There is no inequality, and so strong duality holds, right? By default it holds, yeah. By default it holds, right, because there is no inequality constraint, so there is no problem. Certain condition holds actually. Okay. So, let me write this immediately. Okay. So, check that no inequality constraints are there, and our objective must be convex, right, and norm seems to be convex in xy. It is not even without power, right, it is a simple 2 norm, but without, it should be convex, right, it seems to be. Okay. So, there are 2 things in Slater condition, objective is convex, and the actual condition is that if there is an inequality constraint, then there exists an x for which the inequality constraints become strict. Okay. So, here no inequality constraints are there, and the objective, so objective here is norm x minus y. So, E is convex, there is a question mark here, we may have to actually prove that. There is no square here, that is for sure, and there is x minus y here. So, it is a function of the form, and also there is expectation outside, so that is another level of thing, but I believe that should be fine, right. Okay, so fxy is norm of x minus y. E is convex. Okay, so these verifications are needed. Then if it is, okay, so we can do this as a check, as an exercise offline. Okay, so if it is convex and no inequality constraint there, then Slater condition holds by default. Condition holds by default. So, now for the Slater condition, if you want to know more, okay, because some of you are not much into optimization, but so if you want to do, you just open the book void. You are not at a disadvantage of not knowing this, because questions in exam will not consider this. Okay, only what I teach will matter in exam. Okay, so these are some additional things. You can always like put a star on this material. Okay. So, this Slater condition holds by default, okay, provided this thing matters. Okay. Right. So, the next trick that we are going to do is, obviously we have formed a Lagrangian, and then we want to do a sup of this, inf of this with pi, and then sup to get to the actual optimal value, which is w. So, but we will invoke this fact that strong duality holds, and we prefer to switch the inf and sup because it helps in the calculation later on, we will see. So, using strong duality, to write WPG is now either way it should be okay. Either I do inf sup or sup inf, So it's like inf pi sup of fg, and this is L pi fg, and this is sup fg inf of pi L pi fg. And we have already seen this characterization. When strong duality holds, inf sup can be interchanged. Now, if I look into this, term, right, in the Lagrangian, certain difficulties can arise if norm of x minus y happens to be less than fx plus gy, okay, and that can essentially make this go to infinity. Okay, so I did that proof here. It can go to, yeah, if the inner one is infimum, it can go to certainly to infinity. So we so we have to so let us see why. Okay, so my claim is that if this guy is less than or equal to fx plus gy, then there is a problem that this whole thing may go to minus. It can be made to go to minus infinity. So I will prove that for you right now. Okay, so it's a norm in x minus y, right? It's a distance, right? Distance is always it's a difference between x and y, right? It's not just a norm, it's a difference between first component and second component. That's different from this, that's a little bit different here. I'm not saying whether it's convex or not because I'm not sure. It may be trivial also, I don't know. I'm just raising my hand here, but you try this as an exercise. Yeah, try to take the I think usual definition you should try. Okay, theta xy plus 1 minus theta x1 y1 plus x2 y2. Something should come out. Okay, or Hessian also. Yeah, here there is no square here, so you have to be a little bit careful here. There will be a square root there. Yeah, well taking derivative. Yeah, anyway, like you think over this, that should not be, yeah. Even if it's not convex, you can think of this as, okay, I still want to go ahead. In fact, when people solve things with duality, they do not necessarily ask for strong duality. Okay, so they do not necessarily say that, okay, optimally is this case, but they don't have anything in hand. They cannot solve constraint problem. They will anyway go there, and they are happy even if there is a gap. Okay, because still it's a good approximation of this. But regarding this case, I'm saying that I don't know. We should check that it's convex or not. Okay. So what I was saying is this guy can be problematic depending on whether this is less than this or not. Okay, and I want to prove that that can be yeah, a problem. Okay, so there is a problem. What I want to do maybe is the proof. I will postpone it till the end because my goal is to complete that. So this problem can be proved, but I will make a statement and then say proof next class or today at the end. Okay, so there is a problem if norm of x minus y is less than fx plus gx for some xy in x. And the problem is that it can go to minus infinity because the mass of this, like I'm saying this because I'm not proving this, so it may sound a little bit. So mass of this can be concentrated around some point x naught y 1 naught in such a way. Let's say I have something like delta distribution. Okay, so I will concentrate the mass in such a way, in a very high, that overall this will go to minus infinity. So I will do this proof a bit later. So in this case, if this happens, then the whole the infimum of this will go to negative infinity. Okay, I mean there is a better line in the written somewhere else, so I will just use that line. They don't prove it, but I later try to prove it. So yeah, so what happens is that then we can concentrate mass of pi at xy and send L pi fg to minus infinity. Okay, and the proof later. Okay, we will do this proof later because our theme today is to complete the main thing, and then we will do the theorem proofs, fill up we can do. Okay, so hence what we will assume is that a norm of x minus y is, should be greater than or equal to fx plus gx, and this gives us an additional constraint. Okay, so hence assume norm of x minus y is greater than or equal to fx plus gx for all x and y. Okay, if that is the case, then what can we say about the mean of the Lagrangian, right? Because now two norm of x minus y is greater than or equal to fx plus gx, so that's a positive quantity and it's over the pi. So now if I have to minimize this over the pi, because I am supposed to minimize the L over the pi, if I do that, then the minimum possible value I can have is when pi is 0. Okay, because the integrand itself is greater than or equal to 0, so the area is greater than or equal to 0, so the only possibility is like when I bring it down to 0. So minimum of this is going to be 0 for pi equals to 0. It is achieved for pi equals to 0. So yeah, so with this, the minimum or the infimum of L pi fg is achieved is exactly kind of like just the expectation value basically. So this will be 0. So is obtained, let's say, obtained by taking pi xy is 0. This is the minimum value of pi. The minimum value over pi will be when pi is 0, because if not, then any other positive and integrand being positive, it will give me some positive area. So the minimum area I am supposed to get will be 0 with the integrand being positive, and that will be when pi is 0. Okay, so so at least the sup inf that we have is when, so we did the inf just now. So the sup inf will now become, so inf is achieved, so inf is just this, and then we will add a sup, and that is the Wasserstein approximation, right? So we have the sup fg and inf of pi L pi fg, and this boils down to sup fg and then expectation of fx, x follows p, plus expectation of gx, x follows q. That's it. Okay. And with an additional assumption we had is that we brought in this additional thing. This is when this holds as well, right? So this is the additional constraint is greater, right? Yeah, I mean I wrote it in another way. So is greater, or let's write it in the usual way. So f plus g is less than. So fx plus gx is less than equal to norm x minus y. So this is our existing status, and this is where we are while we are approximating the Wasserstein distance. Right? So this is where we are now. Now the next step is what we said is that we will be looking into one Lipschitz function, right? So far we are here. So the next step seems to be, yeah, it should be g of y, right? It should be g of y, sorry. Thanks. Okay. So if we are our claim in the beginning was we will see Wasserstein distance as a supremum over one Lipschitz function, right? We are quite close now. What we want to replace this is by hx minus gy. Then it will say that hx minus gy is less than equal to norm x minus y. That exactly means those functions h are one Lipschitz. Okay, so we are kind of close, but we still have to do some work. So let us do that. So now, so what we will do now is that we will say that we have to say that this is equal to max over the one Lipschitz functions. So to prove equality, sometimes you prove less than equal and then you prove greater than equal, right? So what we will say is that this is lower bounded by the sup of 1L functions and then upper bounded also, and then in that case it will become equal. So then so we do a lower bound of Wasserstein, lower bound of W1, and this means optimize, convert this to optimize over a class of one Lipschitz functions. So let us start with the expression, and we will say that this expression acts as a lower bound of WPQ. So expectation of hx xp minus expectation of hy yq. This is integral of hx minus hy pi xy dx dy. Now I assume from the beginning that h is one Lipschitz. Okay, so here h is one Lipschitz. Okay, so meaning hx minus hy is less than equal to norm x minus y. So with this we can use that now in the integrand hx minus hy. So this will be less than or equal to norm of x minus y and the joint distribution joint PDF dx dy and that is less than equal to WPQ. Now, if this holds for all H, then supremum should also hold for all H, right? So, since this holds for all H, it should hold for supremum. So, supremum over, so this is how I denote it by being L one ellipsis, okay? And this is expectation of H of X, X follows P, minus expectation of H of Y, Y follows Q, and that's WPQ. If this holds for all H, then supremum should also hold for all H. Okay, that's what we are claiming. So WPQ is lower bounded by this. Now what we will say is that WPQ is also upper bounded by this, and hence WPQ is equal to this. So now upper bound of WPQ. From before, what we have is that WPQ is supremum of fx plus gy is less than equal to x minus y, and this is expectation of fx and expectation of gy, xp yq, and what we want to show is that this is upper bounded by the one ellipsis. Okay, so 1 to so, so to so is that this is less than equal to supremum of one ellipsis functions, and expectation of hx minus expectation of hy, y follows q, x follows p. This is upper bound, right? So this is upper bound and this is lower bound, and combined with this WPQ should be equal. Okay, so this is our 1 and this is our 2, but 2 we have to prove. Yeah. Right, let's see. Okay, pi xy, but you want to
dx dy, we can partition the double integral into two single integrals.
one second, let us do it step by step, right? But then dx and dy are here, right? Okay, so there is dx dy also, and then minus of hy, right? I can, okay, dx dy, okay, and yeah, so we have the first term, yeah, the first term is only the hx term, and yeah, hx dx, yeah, so the first term is just hx dx. Yeah, so I mean we have to marginalize with the pi, right? So we marginalize with respect to x, right? With respect to y to get the x, right? dy and then dx, right? So if I do that, what do I get? Yeah, outer integral over x, inner integral over y, right? Out, right? Yeah, hx goes out, dx go out, and pi integrates to 1, or the marginal px, sorry, marginal. hx goes out, so let us make it outright. So hx dx, and the another integral is pi xy dy. So pi xy dy integrates out. Exactly. Exactly. Okay, thanks. It was a little bit, yeah. So it integrates out, and the same case here, it also integrates out, and hence there is no role of pi on the left hand side. Okay. So hence I can still do this, and still get less than equal to WPQ. Okay, that's okay. Okay, so so as we conclude, like, this itself is not clear. This step, okay, is not clear, but what is clear is from here to here we do have, which we just have, right? Everyone okay with that? This was a nice thing to. So the marginal goes out, there is no role of the marginal anywhere, which marginal, I mean the pi has no role, and then this inequality holds. Now let us do the upper bound quickly, and then we are essentially done with the. So this is the supremum, and we have to show that the same thing is also upper bounds this. Okay, that's what we have written there, and there is a. So let me use. Okay, 10, 11. Okay, lower bound, upper bound. Okay. Oh, we have 12. Yeah. So for the upper bound, we use something called it's called infimal convolution. So let us try to do the upper bound. I will take like 10 minutes or something. Okay, looking at the material. So introduce infimal convolution, and to this define kx as infimum of u, norm of x minus u minus gu. Okay, we define this to prove this upper bound. Okay, so our claim is that k will be. Claim is that k is 1 ellipsis. So kx is less than equal to. So if I kind of instantiate this infimum by some x, then k will always remain a lower bound. So x minus u minus gu, and I introduce add and subtract y. Okay, so and then use triangle inequality. So add, subtract y and triangle inequality, then I get y minus u minus gu. Okay, add and subtract and triangle inequality. Now, yeah, the above holds for any u. Okay, so above holds for any value of u. Now, so this implies, so kappa x or kx is less than equal to 2 norm of x minus y plus infimum. So since this holds for any u, it should also hold for infimum of over u. So this is norm of y minus u minus gu. And this must be equal to again, like I can replace the other guy by ky according by definition of the kx. This is infimum, this is exactly ky. So this is Okay, so this implies kx minus ky is less than equal to y is less than equal to norm of x minus y. And similarly, we can prove the other way also. You can switch the role of x and y, and you can also prove ky minus kx is also so similarly ky minus kx is less than equal to norm of x minus y. So together we can say that mod of kx minus ky is less than equal to x minus y. So this implies mod of kx minus ky is less than equal to x minus y. So now our I is at this fx plus gy is less than equal to norm of x minus y. So okay, so if fx plus gx is less than equal to norm of x minus y for all x comma y, then for all v, we have fv is infimum of u yeah, so then for all v, we can write fv is less than equal to infimum over u of norm of v minus u minus gu. It's, is that a correct statement? Fv is, yeah, if this is true, then for all v, we can write Fv is less than equal to infimum of v minus u minus of gu. Basically, I replaced x with v and fx plus gy, right? Keep making this mistake. So if this is true, then this is true also when x is replaced by v. And I can also do it for all, and that is true for all and y I can take to be u, and since it's true for all y, okay, so I can do this very quickly. Okay, so fx is less than equal to norm of x minus y minus gy, and this is true, so set x to be v and y to be u. Okay, so then we have fv is less than equal to v minus u minus g of u. Okay, and this is true for all u, so this implies fv is less than equal to infimum of v minus u minus gu. Okay, this is what we did here. We use the fact that f plus gy is less than that. Okay, so but this v minus u minus gu can be seen as kv. Okay, according to the way we define k. Okay, so this will be, I have not kind of rubbed this, right? So kx is infimum of norm of x minus u minus gu. So this, we can see this as kv. Okay, so in place of x I put v, then it's exactly kv. Now this is less than equal to, so kv is infimum, right? So since it is infimum, if I instantiate x by u, then that will be greater than kx. Okay, so this implies k u. If I put a x to be u, so choose x to be u, then for that k u must be less than equal to, so u minus u goes away, right? So this is exactly what I'm going to write here. So this is less than equal to norm of v minus gv. So this is equal to minus gv because this goes away. If I choose v to be minus y, for v to be minus y, then I have minus ky is greater than equal to gy. Okay. So choose v to be minus y, then from here, right? So this inequality that I have, k is less than equal to g. So minus k is greater than equal to g. So in place of v, I choose y. So that's how I get this. So then all this implies that expectation of fx plus expectation of gy and x follows p and y follows q, and this is less than equal to, now fx, from here we have seen that fx is less than equal to kx. Okay, in place of v I can put x again. Okay, so this means that this fx is less than equal to expectation of k of v. So expectation of, I mean k of x, and this from here I can say, so from here I have that gy is less than equal to minus ky. So this is plus, or I can put the minus outside, right? So minus expectation of gy. Right. So then what we can say now about WPQ is supposed to be supremum of these left quantity with fx plus gy less than equal to this, and then that translates to the upper bound for the right hand side. So and k is one ellipsis we already have shown. Okay, so all this we combine now. Okay, so this implies WPQ, which is supremum of fx plus gy is less than equal to norm x minus y. So what we have seen from there is that expectation of fx plus gy is less than equal to expectation of kx plus ky minus ky. And where k is one ellipsis, right? So this is less than equal to. So since I am taking supremum, I can take supremum both sides there as well. So this is supremum of, and I can replace k by h also. Okay, so just for the usual notation. So ax minus this is less than equal to norm x minus y, expectation of hx minus expectation of hy. And this we have shown before is less than WPQ. So we have shown both ways now. We started with WPQ and we ended with WPQ. So what it essentially says is that WPQ must be equal now to this. Okay, so this was the Kantorovich result that we have just shown. So I'm just trying to kind of and I can also replace this by same as h. In the original notation we wrote like this in the main theorem. So this is exactly what we proved. Okay, so hence we have proved that WPQ is equal to supremum of norm h 1 ellipsis. Okay, so and then expectation of hx minus expectation of hy. Okay, so this is the result that says that Wasserstein distance that initially was on infimum of the joint distributions and so on reduces to supremizing over 1 ellipsis functions and calculating the distance, and obviously this x follows p and y follows q. Yeah. Where did we use? K, right? I replaced k by h. I replaced k by h here, that's it. I mean, this is less than equal to, right? I took a supremum of this. This supremum is the Wasserstein. Yeah, I mean, the constraint here, and this
satisfies that constraint, right?
as a subset, it does satisfy.
Yeah, so if it's a subset.
Here, there is a little bit like it's not a mod here. But mod, is it exactly same, right? Does fx plus gy less than this imply that it's the same thing as, I mean, the special case is mod of hx minus hy is less than x minus y. Two special cases, I mean, I see I can take g to be minus h, I agree. There is no restriction on that, and from here I can instantiate this by saying that let me take g is minus h and f is h. So in that case, this supremum will be less than equal to supremum over the restricted set, which is h x minus h y less than equal to norm x minus y. And what I want is also, yes, that's the argument also, right? Because the set is decreasing, then supremum actually can decrease.
Yeah, so
That's not that obvious, right? Yeah. Yeah, because we are yet to take supremum also, right? We didn't just instantiate, but we have to take supremum as well. And if we take supremum, we are supposed to get lesser, not more. But if I instantiate, then I'm not supposed to take supremum, obviously. Then I'm saying, okay, just instantiate, then I certainly get something which is lesser. But here I'm supposed to take the supremum. Yeah, I think it's okay. So we have proved this Kantorovich theorem, and there is just 1 or 2 lines left actually if I have to write the GAN, because GAN just tells us that now it's all about what you feed in here. You parameterize this as a neural network, okay? So you take y to be output of some feed forward network, let's say z, and that takes y is equal to theta of z, okay? And then here also you parameterize this by a neural network, okay? So it's similar to the GAN where h acts like a discriminator, okay? So if I have to instantiate this with for WGAN, the main part kind of is done where you have a variational approach where you are allowed to vary h, okay? And you keep h to be 1 ellipsis, okay? So these are the constraints you have to set. Okay? You have to put a bound on that, and so if you are doing a practical implementation, then you have to do some gradient clipping and so on, okay? Because h must be kind of constrained. So if I have to just write down the main GAN objective, the WGAN. So consider a parameterized family of functions. Okay, in this case, like we are changing the notation a little bit, so it's like HW parameterized by W, and W are the weights, parameterization weights, and the very popular ones are like, as I said, we use neural networks usually. So, and these are what WGAN says is that although you are supposed to take one ellipsis, but even if you take k ellipsis, okay, it should not matter because it will be up to a constant factor. It will be giving you a similar distance. So in general, there is they remove the restriction that it's one ellipsis, but they say it could be k ellipsis. Okay, so family of this are all k ellipses. Okay, instead of one ellipsis. So then in that case, the objective that we have is W in W, and expectation of x in P, and then minus expectation of Z PZ, and then HW G theta Z. So as you can see, for H we have chosen some parameterized functions, and as I said, once you choose a parameterization and so on, you may not have this equality because those parameterized networks are a subset of these. Okay, so at the end of the day, you will be approximating the distance here because you will take certain functions which are a subset of the original. So so HW is the choice you have, and also the way you have Y is via another neural network which is G theta, and Z is a known random variable. So as I said, we are building a generative model, so we want to produce Y via a push forward which is GZ, and Z is known random variable. Okay. So the training procedure goes as it's done in the GAN, and remember that this is just the max part, but then in the WGAN we actually have also the infimum involved. Okay, infimum over all this as a final step. So overall, it will be also an infimum over theta. So now W is, so in the WGAN they call this as a critic. Instead of discriminator, they call it critic, and this they call it generator. For all, what is the Wasserstein? We are supposed to minimize the W, right? Right. Why should I? This is a minimization over all P and Q, right? Minimization over all P and Q, hence we have to have the infimum as well. Okay, that's how we get to the, because at the end of the day, Wasserstein distance here, what does it do, right? It's a true distribution, and let's say Q is the P theta, right? In our original notation, if we have W P theta. Now this is what we want to do, right? Minimize what is the possible theta for which I am estimating a P theta, and P theta is estimated essentially by the generator that's trying to learn the distribution that I have, and this is the critic that will judge whether the samples created are correct or not. Okay, so overall we put this theta because of the fact that we have estimation going on here for a better P theta. Okay, so I believe the class is going longer. So then expected. So now from here the training procedure is very easy. Okay, it's same as the GAN. You do gradient ascent descent because you have max over W, so you do gradient ascent. When you do the max ascent, then you have to take gradient of this and this as well because both have W. If you do the descent minimize with theta, then you are supposed to just take the gradient here. That will be your descent, right? So that's how we get the do the training. Okay, that's the training part of the GAN, and I have the algorithm, but I can write this algorithm in the next class, right? It was quite long today. We got stuck somehow. That was the Okay, but we got the main thing. Okay, that's WGAN. Okay. Yeah, like I almost